The 90% idle problem. Modern Blackwell Ultra clusters spend 92% of their clock cycles waiting for data to arrive from HBM4 memory. We are effectively paying for trillion-dollar compute farms that function as expensive space heaters, while the actual logic units sit idle. This is the memory wall, and in 2026, it has finally stopped scaling. To understand why your local inference is stuttering despite the hardware upgrades, we have to look at the von Neumann bottleneck. The high cost of data movement. The fundamental problem is the physical distance between the processor and the memory bank. Even with the tight integration in the latest chiplet designs, moving a single bit from memory to the arithmetic logic unit consumes orders of magnitude more energy than the actual computation. In 2025, the industry tried to solve this with larger L2 caches, but as model parameters crossed the 10 trillion mark, the cache miss rate became a performance floor that no amount of clock speed can penetrate. We are hitting the limits of electron mobility on a silicon substrate. This physical limit is exactly why the latest throughput benchmarks for the Llama 4 series show such diminishing returns. The utilization collapse. Look at the actual utilization data from the latest ML-perf results. While the raw flops on the spec sheet have tripled since 2024, effective utilization during large model inference has dropped by 40%. We are seeing a divergence where the hardware is technically faster, but the system latency is dominated by DRAM refresh cycles and bus contention. Since we cannot move the data any faster, we have to stop moving the data entirely. Mechanics of processing in memory. Processing in memory, or PIM, shifts the architecture from a central hub to a distributed logic model. Instead of dragging weights across a silicon bridge, we are now embedding simple logic gates directly into the memory layers of the HBM stack. This allows for massive parallelization of the matrix vector multiplications that define transformer layers. It is not about raw speed. It is about reducing the energy cost of data movement from picojoules to femtojoules. The latest white papers from the Samsung and SK Hynix joint labs show this reduces total power consumption by 60% for reasoning models that require high token output. But PIM requires a total rewrite of our software stacks, and that leads to the real bottleneck. The part no one wants to say. The transition to processing in memory reveals that our current software optimization era is over and a hardware-defined era has begun. Because we reached the physical limits of data movement in 2026, as seen in the utilization collapse of the Blackwell series, the industry can no longer rely on CUDA kernels to mask architectural inefficiency. For developers, this means the end of general-purpose compute dominance. You will soon be forced to choose between high-precision training chips and specialized PIM inference silicon that cannot run standard code. For researchers, this shifts the focus away from model size and towards sparsity and architectural density. We are moving from a world where we throw more compute at the problem to a world where we must engineer around the cost of moving a single bit. Watch for the first commercial PIM-only edge devices to drop in late 2026. They will define the price per token floor for the next 5 years. Subscribe for more.